So, all right. So this will be the last class on this. So what I did last time. So since there was a class skip, so let me quickly recap. So last time we proved the hypercontractivity, only a special case of it. The hypercontractivity lemma says that this Qt is a contraction even from P to a slightly larger Q. How large depends on T. Okay, so you can put it in two ways. You fix a P and fix a T, then there is a Q which is slightly larger than P for which this holds. Or you can fix P and Q and then say that there is sufficiently large T for which this holds. Okay, so either way, we only were interested in the P equal to 2, Q equal to 4 case, which says that Qt from 2 to L2 to L4 is a contraction. Okay, so I proved it last time, the 2,4 hypercontractivity theorem, that QTF L4 is bounded by L2 or norm of F. As long as e to the minus t is smaller than 1 over square root of 3. That is what comes out of the square root p minus 1 over q minus 1 is the general number. So we proved this by induction on the number of variables. Okay, so that's what we did. As a corollary, I gave one simple corollary is f is a homogeneous polynomial of degree k. So if f is like this, only Fourier coefficients of order k survive. Then what does the qt apply to this do? Qt is just, I also write rho for e to the minus t. All these get multiplied by rho to the power k. Since it's homogeneous, that rho to the k comes out. And you just see that tf is just go to the k times f. So what you get is an inequality between L4 norm of f and L2 norm of f. So you get that L4 norm of f is bounded by 3 to the k by 2 times L2 norm of f. These norms are in the triple norm, that is with the probability norm. Okay. So, and I gave an exercise. Actually, this is the exercise that this is what we will use. So we will be using this exercise rather than the 2,4 hypercontractivity theorem. I do not know if you can deduce this exercise from there. So this is in O'Donnell's book, he calls it Bonami's lemma. So it's called Bonami's lemma, and that's what is used for some people who are in computer science and other on. You may have heard, if you have at all looked at any of this Boolean function business, you may have heard the term Bonami-Beckner inequality. It is the same, but Ryan O'Donnell makes, he looked into it rather well, and then he makes the case that this should be called just Bonami's. If anyone has seen Bonami-Beckner before, it's pretty much the same thing. Maybe there is a slightly more general point, but that's also he calls Bonami's lemma, actually. Anyway, so this is the exercise we are going to use, that if f has degree at most k, then L4 norm of f is bounded by L2 norm of f times 3 to the power k by 2. There is a bit noise for some reason. Is somebody unmuted? So let me just see. There is a little bit of disturbance. So
looks like Srikanth is unmuted.
Okay. No. Okay. Sorry. Yeah. So yeah, so that is what we are going to use, and I don't see how you deduce it from the earlier one. I don't know, but you can follow the same proof. Okay, so you can follow the same proof by induction and so on. So, and I indicated another possible proof. Let me not waste time on that. So let's proceed. So now, what we want is to prove the so now I want to go back to the proof of the robust version of. What I want to do is the stability version of Arrow's theorem, and I already did a little bit of groundwork there. So let me recap that point. So let's recall the theorem first statement, that this is if f is a Boolean function such that in a three-way election using f, probability that there does not exist a Kondo set when is small, then f is actually equal to a dictator function or an anti-dictator function on a large set. That is, there is a set with small proportion. Its proportion is only some, I have written 10, it's not really 10, it is some constant delta 2 to the n, such that outside of that it is either xk everywhere or minus xk everywhere. So it's more or less the dictator function. And I argued the point that since the Boolean functions, this is not different from or any stronger than saying that the L2 norm squared is, that is 1 over 2 to the n, this norm squared is bounded by 10 delta. Okay, so this 1 by 2 to the n times this is exactly L2 norm, I mean the triple norm squared if you want. So 1 by 2 to the n, f minus chi k or f plus chi k, one of those two has squared L2 norm bounded by 10 delta. Okay, so we will take, that is the way we will prove it. So, and very quickly recapping how do we go about proving such a thing? You have to prove f is close to some dictator function. So first of all, we took the formula for probability of no Condorcet winner. It was, and we showed that it's a slight improvement of what we did in the Ayos theorem proof. We needed to be a little more quantitative, but we got that probability no Condorcet winner is at least 2 over 9 times 1 minus the sum of squares of the Fourier coefficients for singletons divided by 2 to the n. So because of that, if that probability is small, that means this has to be close to 1. So if probability no Condorcet winner is less than delta, then this 1 over 2 to the n summation f hat k square is at least 1 minus phi delta. I have written n 9 by 2 is like at most 5. So it's at least 1 minus phi delta. Okay, another way to say it is that if you take g to be the function built out of f, by taking only those coefficients, you remove all the other Fourier coefficients. Okay, only keep the singleton Fourier coefficients, then g and f are close in L2 norm squared. That f minus g L2 norm squared 1 over 2 to the n is basically the sum of squares of all the remaining divided by 2 to the n. So that will be at most phi delta. Okay, so since f has L2 norm squared 2 to the n. So this is something that we already know. So the first step is going to be in the robust version, we replace f by g and f and g are close. Now the thing is g uses only the one level Fourier coefficients. We have to show that in fact only one of them matters, all the others are small. If you remember Ayos theorem proof, that's essentially what we did. There the probability was 0 and by argue there, so f would be the same as this. And then since f is Boolean, we could argue that exactly one Fourier coefficient is non-zero, the others are 0. Here, we only know that this is actually f and g are close. F is a Boolean function, g is not a Boolean function, but f and g are close. From that, we have to argue that only one of these coefficients remains and the rest are small. Okay, so that's what we want to do. Already a little bit of groundwork was done for that also, but maybe I'll go back to, so I gave you a kind of heuristic, not a proof that if you assume G is bounded, G is not a Boolean function. Actually, it can be quite large also. But if mod G is less than equal to some fixed number, then we can actually show that G square minus 1 is bounded by f minus g square, and so that will be small. And what I did earlier was that, okay, so basically what I showed, I'll come back to this maybe after the proof, but if you can show that this thing is true, that g square is close to 1, in this sense that g square minus 1 L2 norm squared by 2 to the n is at most some constant delta. From there, we can deduce that actually one of the coefficients is large. Okay, maybe this is something I will come back and recap. Okay, so but the point is to show that g square minus 1 L2 norm squared is smaller than 45 delta times 2 to the n. And this proof that if you assume g less than 2, then it is okay, otherwise it's not true. So that's where we have to use the hypercontractivity of Bonomi lemma. Okay, so now I will go to that proof, but before that, any questions so on this? Okay, if not, let's go to the proof. So we have to show somehow. So let me just rewrite that, just those definitions. So f is yes, and G uses only the singleton sets. Okay, and we have seen, we know using F, this implies that some constant times delta. So I had some 45 delta there, so whatever it is. Okay. So now what we want to show, the goal now is show that G square minus 1 L2 norm square divided by 2 to the n, this is the triple norm really, is less than equal to some constant times delta. Okay, so this is what we want to show. How are we going to do that? Okay, so let's do that. So let's write it. So the left hand side 1 by 2 to the n is well, okay, this is really, if I use just a probability language, I think if people are comfortable, then this is just a bit simpler. Let me just use it like right like this: expectation, where expectation is expectation with respect to uniform measure. Uniform probability measure. So we will write it as expectation of G square minus 1 squared into indicator mod G less than equal to some constant m plus the expectation G square minus 1 the whole square into indicator mod G bigger than m. Okay, where m is such that, so what is this m? Okay, I will write down, in fact, it doesn't depend on any other choices. It's the probability that mod G, see, now we are thinking of G as a random variable. Earlier we saw that if G is bounded, then we are good. I mean, bounded means if you have a uniform bound which doesn't depend on n and such things. If G was bounded by 2 or by 10, it would be okay. So what we are going to do is actually it is motivated by that. So this m you choose, so that probability that this bigger than m is sufficiently small. Okay, how small? I will put down. Okay, so I will put down this number. I think it may be okay. What this is we'll come back to. It's something defined in terms of this constant c. Okay, so we'll make it smaller than, just for a moment, let me write it is smaller than 1 by c. Maybe it is different, but where this is the c, okay, this constant c. Okay, so what then? So first of all, this part, on this, we will use the similar idea. So first term, how do we control the first term? So we use the similar idea to before. Okay, so on G square minus 1 whole square, we will first write, I don't need to go back there. I will just do it again. G minus 1 into G plus 1, right? So we have G minus 1 square into G plus 1 square, right? Now, since G is bounded by M, this G plus 1 can be bounded by M plus 1. M plus 1 into, and G minus 1 can be bounded by G minus F square, okay? So what we are using is G plus 1 is less than equal to mod G plus 1, which is less than equal to M plus 1, and G minus 1 is smaller than G minus F, because F is plus or minus 1, right? Sorry, is this correct or am I making a mistake? Sorry. Okay. If so, this is if G positive. This we do if G positive. If G negative, you do it the other way. Okay, okay. Sorry. So the way. So this is. So actually, strictly speaking, so this is. We use this if G is positive, and if G is negative, we use it the other way. We bound that G minus 1 is bounded by M plus 1, and G plus 1 is bounded by G minus F. Okay, so this is the way we will do. Okay, so I hope it is okay. Is this all right or not? Am I making a mistake? See, when G is positive, G minus 1 is the smaller of the two, G minus 1 and G plus 1. When G is negative, G plus 1 is the smaller of the two. So the distance from G to F will be at least the closer of the two, right? G minus 1 and G plus 1. So that's all. Okay. So this is okay. So consequently, this can be bounded by M plus 1 whole square times right. So M plus 1 whole square times what is that? Phi delta, right? Okay. Yeah, because this is already dividing by 2 to the n, so this is bounded by phi delta. Okay, we get this. Now second term, what can we say about the second term? That is, there we will use by Cauchy-Schwarz. First, let's use Cauchy-Schwarz. Is smaller than G square minus 1 to the power 4 square root and square root of the expectation of this square, which will become probability mod G bigger than M. And so this is now here is where we use Bonami lemma. Okay, so G square minus 1. So you notice that G square minus 1 has degree less than or equal to 2. G uses only degree 1, right? G is of degree 1. G square minus 1 has degree less than equal to 2. And what does Bonami lemma tell us? The Bonami lemma tells us that if the degree is at most 2, then the L4 norm is bounded by L2 norm times 3 power k by 2. Okay, these are the triple norms. So we get that this expectation is the triple norm. Okay, that has the 1 by 2 to the n. But we are not raising to the power 1 by 4. We are raising to the power 1/2. So what do we get here? Square root 3 to the power 2 is what? So what we have is expectation G square minus 1 the whole square. Oh, sorry, to the power 4 to the 1 by 4 less than equal to square root 3 whole square. Expectation G square minus 1 whole square 4 to the power half. This is the Bonami lemma. Because the degree is 2. So what is it? What is the bound for this? Square root 3 square is 9. I'm going to square this, right? So I get 9 times expectation G square minus 1 the whole squared times this probability I want to be, yeah, so sorry, but 9 times that times square root of probability mod G bigger than M. So, okay, sorry, that was not related to that C. Actually, that C is in the conclusion. I wrote something here. It's not 1 by C. It's a pure number I can write from here. I want this to be smaller. So I want to write this is less than equal to 1/2 expectation of g square minus 1 the whole square. So what is this? So I want this to be smaller than how much? 9 by, I want that to 9 into
1 by 18 or whatever.
1 by 36, right? Oh, sorry. No. So I want this to beat 9 square into. Yeah,
So it's like 1 by 18 squared, no?
Yeah, 1 by 18 square, which is what I'll write here. So this is what I want here. I want this to be smaller than 1 by 18 square, then this expectation will be this small. Okay, so first term is bounded by this, second term is bounded by this. Now transfer this here. So this is actually what is on the left side, right? Expectation of g. This is actually expectation of g square minus 1 the whole square. This to transfer to the other side, we get 1/2 is bounded by this term. M plus 1 squared into phi delta. So which is same as expectation g square minus 1 square less than equal to c delta, where c is m plus 1 square into 10. Okay. Now, if you go back to what I did earlier, once I have expectation g square minus 1 whole square bounded by a constant delta, then from that we get that the variance is g square is also bounded by the same, and we just use the expansion of g square, Fourier expansion of g square, and write variance as the sum of squares of the non-constant Fourier coefficients. Okay, so we got that way we got that variance g square is something 1 by 2 by 2 to the 2n 2 to the 2n minus the fourth powers of f hat j, and so you get the fourth powers will be at least so much. Okay, instead of 45 by 2 you will have that other constant whichever we got, and because this sum of fourth powers is bounded by the square of the maximum times sum of the squares, you get that the maximum Fourier coefficient, you even take 2 to the n by 2, which is part of the expansion inside here, maximum of these coefficient square is at least 1 minus this constant delta, from which you get that if that is the first one, then you get that one of the coefficients is close to 1. So the rest of them will be small, and you get that f is close to chi 1. Okay, I hope you remember this. So does that complete the proof? Together with this.
Yeah, but this C, it should depend on whatever that M or whatever you chose.
So,
that will depend on L1 norm of G, right?
Right. So this is an issue. So this is not an actual proof actually. So this is actually, so the C should not depend on N or anything actually. So, okay, so the C should not depend on that. Only issue is that. So this C, how do we get that C is not, I mean, so this M, so C depends on M. So, but caveat, so C depends on M. And M depends on G. Which depends on F, of course. So, which depends on F. That's not good. So, we should not let it depend on that. But what we can do is, but we don't need that. So, in fact, it doesn't, because what we know is that, okay, so L2 norm of G, okay, is bounded by L2 norm of F plus L2 norm of F minus G. Now, this is So if I divide by 2 to the n, L2 norm of G is bounded by, this will be 1 plus 5 delta. Okay. So this is some fixed number. So let's say it's less than equal to 2 if delta is small. Anyway, we care about only small delta. I mean, it doesn't matter. You keep 1 plus 5 delta, it doesn't matter. But we only care about small delta. So this is bounded. Now you can use Chebyshev to get a m, which doesn't depend on anything, right? So probability mod G bigger than m is bounded by expectation mod G squared divided by m squared, and this is bounded by 2 over m squared. Hence, we just choose m square bigger than how much? We wanted that to be smaller than 18 squared. Hence, m square bigger than 2 times 18 square will do. So there is no dependence on anything. Okay. Is this okay? Kaushik?
Yeah. Thanks. So here we just use f is Boolean, right?
F is Boolean. F
yeah,
is
okay.
Boolean, so its L2 norm in the normalized sense is 1. And
Right.
F minus G, we already showed that it's normalized. Okay, actually, sorry. I made a mistake here. This was for the squares. This was for the squares. Yeah, so, okay, so let's put, if you want, 2 times this plus. It's less than that means square is less than 2 times that plus 2 times that. So you'll get an extra 2 here. Okay. So, but this is for the, sorry, this is how way we should write. This is the expectation squared. And then it is okay. I mean, so it's not, maybe it is an extra 4 or something like that. Okay.
Yeah, that is fine. Yeah.
So I forgot the square actually, but otherwise it's okay. So you get something like this. So this completes the proof actually. So we have shown that one, so from here that expectation G square, so consequently expectation G square minus 1, conclusion is bounded by a constant delta, and we have already seen that this implies that one Fourier coefficient is greater than equal to 1 minus some other constant times delta. It's close to 1. So there is some Fourier coefficient which is close to 1, from which we immediately get that f is actually close to chi k or chi minus chi k. This close is L2 or other sense. I mean, we know that L2 sense is equivalent to the sense given in the statement of the theorem. Okay, that completes it. Any questions, comments, anything? So this is the robust version of Arrow's theorem. Stability version or robust version, whatever you want to call it. So I mean, this is all I wanted to do in this Boolean function business for now. Probably forever. I don't think I'll come back to it. There are very interesting things in Boolean functions, but they are more on the probability side, and to appreciate them requires having seen some amount of probability, some of the interesting problems of probability one studies in these times. So that's why it's not something I want to do. I also don't know too much, but I could learn and do, but it may not make sense in this audience. Yeah. So I will end it here then. But if there are any questions, now you can ask, please. Okay. If there are none, then we completely change directions and go to some another area. which is in number theory, very famous theorem, amazing theorem of Dirichlet. Okay, so we go there. So today I will just give the introduction, the theorem statement, and some ideas. We'll take a few lectures. It always takes more than I expect. So let me not say how many lectures I expect. So, okay, what is Dirichlet's theorem? So everyone knows that if you take, we know from Euclid that there are infinitely many primes. Okay, so I assume everyone knows a proof of this. Is there anybody who hasn't seen a proof of this? There are lots and lots of proofs of this. There are many interesting proofs of this theorem. So, Euclid's original proof is one. That's not so. Just for fun, let me tell you another proof, which is not so well known. It's actually somewhat, since many engineers, it's a bit of question of. It's a bit like information. Okay, so it's a question of information in a way. So this is a proof due to Gregory Chaitin, and it's actually similar to a proof that Paul Erdős gave. But I'll give you the proof due to Chaitin, just because some of you are engineers and you may enjoy this proof. So here is a proof. Suppose there were only k primes. So let us write P1, P2 up to Pk. Suppose there were only k prime numbers. Okay. So what we can do is every number can be written as a product of prime powers, right? So the fundamental theorem of arithmetic says that you can write it uniquely as a product of prime powers. What we use is even weaker, that every number can be, this will assume that every number can be written as a product of prime powers. Class. Class. So every number can be written as a product of prime powers, right? So let's forget 1. So for example, 2. Let's say 2. We will write the exponents. Okay, so we'll write it as 1, 0, 0. Okay, so and so on like this. So 3 will be 0, 1, 0, 0, 0, 0 like this. Okay, 4 will be exponent 2. So P1 is 2, prime number 2, P2 is 3, and it goes on up to some number. Okay, so 4 has 2, 0, 0 like this, right? So you agree. So every number, if n is of the form, if we can write n in the form P1 to the, let's say E1, P2 to the E2, Pk to the Ek, then you will just write here E1, E2 up to Ek. Okay, so we can write like this. For every number, we can just write the exponent. So every number is represented in this table. Okay. But now look at all numbers n less than equal to some large number 2 to the m. Okay, so let's look at this 2 to the m. Okay. So let's only look at this table up to 2 to the m. So how many numbers are there? So there are 2 to the m numbers, right? Okay, maybe one less because I left out one, but there are 2 to the m numbers on the left side. But how many tuples are possible? How many possible tuples are there? See, each of these exponents, how big can it be? N is at most 2 to the m, right? So no exponent can be more than m. Do you agree? So all EIs, no exponent can be more than m, right? Because all the if you have more than m, then you get something bigger than 2 to the m. So each of these EIs is at most m. And how many tuples can I make? Each of them can be 1 up to m. So there are m to the k many possible tuples. So how can you represent 2 to the m numbers with m to the k tuples? For large m, this is not possible. So not possible. Okay. So this is a sort of, I mean, it's information in the sense that you don't have enough information. If you had only finitely many primes, you don't have enough information to represent all the integers. That's a kind of proof. What is actually more relevant is a different proof of very much relevant is a different proof of, there are hundreds of proofs of this infinitely many primes. Okay, I think 100. 100 may not be an exaggeration actually. There may actually be 100. So there is a book called Proofs from the Book, which some of you may have seen. There I have seen 7-8 proofs of infinitude of primes. Anyway, so the Euler did something else actually.
Sir.
Huh, yes.
Euclid's proof doesn't use this fundamental theorem of arithmetic, right? We don't need to assume that.
No, it uses that every number is divisible by a prime number, right? It does assume that you can, so because you take the product of P1, P2, Pk plus 1, right? So it doesn't say that's a prime number. It says that has to be divisible by a prime number.
Yeah, so it is not divisible by any of P1 through Pk.
Yeah.
So there has to be some other prime, or this itself has to be prime.
But so you're assuming that any number is divisible by a prime number.
Yeah, but that doesn't require fundamental theorem, right? That's just by definition of a prime.
No. Definition of a prime is that it is not divisible by anything other than itself and 1.
No, but so you have a number, so either it is composite or it is prime.
Yeah, right. But that is more or less what is used here also, is all I'm saying. It's not the full fundamental theorem. Full fundamental theorem says that you have to so see, once you have a prime factor, then you divide and you have another prime factor and you can go on. So you can write n as a product of primes.
Yeah.
So
no, but here we rely on the fact that that representation is unique and all that.
no,
right?
we don't rely on that it is unique. This could be some representation. Okay, doesn't matter. All I need that n to this tuple is injective. If you look into it, I'm not using that. If there were multiple representations, it would only make things worse. What you are using is that two tuples, the same tuple can't give two different numbers. That is clear, right?
Yeah.
So that's all we are using. We are not using the uniqueness.
Okay. Thanks.
Yeah. So Euler proved that summation 1 over primes. So whenever I write in this entire section, we write P means prime, okay? Without any exception, P will be prime. I won't write that. So sum over P is actually infinity. So this is a great fact. So that sum of the reciprocals of prime numbers is infinity. And that is how this is a matter of great consequence. So note that for any alpha bigger than 1, sum over primes, 1 over prime to the power alpha is bounded by sum over all integers to the power alpha, right? Because primes only form a subset, so that is finite. So somehow the primes also, they start diverging at exactly the same place, sort of, at least at this crude level. For powers bigger than 1, this is finite, and for power 1, it is infinite. Anyway, this, by the way, implies, of course, that the sum of, there must be infinitely many primes, otherwise this, hence, so this of course implies there are infinitely many primes. It is a much more quantitative thing actually. In fact, this is more or less suggesting to you what is the prime number, or suggesting something to you like the growth of prime numbers. Prime numbers, so this is great information actually in this analytic information. So it shows that primes cannot go like n squared. For example, pk cannot be if we order the primes, p1, p2, p3, and so on, pk cannot be going like k power 2, because then the sum of reciprocals would have converged. Pk cannot even be going like k to the 1.1, then the sum of reciprocals would have converged. So pk has to go, we know pk is at least k, right? So pk is at least k, and pk is going so slowly that the reciprocal still diverges. So pk cannot even be going like k times log k square, right? I mean, we don't know whether pk's have a actual behavior, but if you assume there is a behavior, this shows that you can't even summation 1 over k times square of log k is convergent. Therefore, even that cannot be the case. So this is actually almost, if you know that, so if you take summation k times log k to the alpha is infinity if and only if alpha bigger than 1, right? So you may know this. Otherwise, prove it. Because of that, hence, this theorem is strongly saying that pk cannot be going like k times log k to a power bigger than 1. So, and you can do finer and finer, and it is starts more and more suggesting that pk must go like k log k, which is equivalent to prime number theorem, that number of primes below x is x over log x. So that's there is a great deal of power in this analytic statement. It doesn't tell you anything about the constant and so on. But anyway, this is actually something going to be relevant to us. But before going to all that, what is Dirichlet's theorem? Dirichlet's theorem is the following. So suppose we take a subset. Consider an arithmetic progression. AP is arithmetic progression. So A plus D in natural numbers, okay? So are there infinitely many primes in this? So the question is, are there infinitely many primes? In this arithmetic progression? Okay. Sometimes no. I mean, you can think even numbers, for example, form an arithmetic progression. That would be stupid, right? So no for trivial reasons. Example, if A is D is 2, then you get 2, 4, 6, 8, etc. Only prime number is 2. There are not infinitely many primes. Of course, it would be very stupid. So one should assume there are obvious obstacles. If there is a common factor, then there is something number that divides all of them, then there will be a problem. Assume that A and D are coprime. That is, no common factors. So A comma D is the notation for GCD. No common factors other than 1. So then the answer is yes. And this is what Dirichlet proved. See, if the answer was no, it would have been a tremendous theorem also. Okay. For example, so let's take an example. So let's take two arithmetic progressions. So 1 mod 3 and 2 mod 3. Okay, there is also 0 mod 3. 0 mod 3 are 3, 6, 9, 12, these numbers, and then 1 mod 3, 1, 4, 7, etc. and 2 mod 2, 5, 8, dot, dot, dot. Of course, we don't expect, I mean, so this cannot have this because of the same reasons. All of them are divisible by 3. Only one prime number is there. Forget that. So question is, are there infinitely many prime numbers here and are there infinitely many prime numbers here? If that was not the case, that would also have been a very great theorem, meaning you would have found a pattern in prime numbers. If suppose there were not infinitely many prime numbers here, then you would say that almost all prime numbers have to be 2 mod 3. That would be very strange, and there has to be some deep reason why that such a thing is true. But what Dirichlet's theorem is saying that no, there are no such, other than the obvious thing that this cannot contain infinitely many arithmetic primes, you don't have any obvious patterns. Okay, so okay, this is also a great theorem. That would have been a great finding a pattern in primes. This is saying there is no non-obvious pattern in primes of this kind. Okay, so that's what Dirichlet says. If A and D are coprime, then the arithmetic progression contains infinitely many prime numbers. So this is sometimes called the starting point of analytic number theory. It is a really amazing, not only the statement, but the proof is amazing. So to my knowledge, there are no elementary proofs either like this or Euclid's proof. There are for specific cases. For 1 mod 3, 2 mod 3, there are some elementary proofs, somewhat like Euclid's proof at least. But for general one, I am not aware that there is any such elementary proof. So well, the proof we will give is the real proof, and it is actually a very deep one. Okay, so we'll do that, and it will use Fourier analysis of Z mod n. Okay, so that's what we will do. So how is this? In fact, what he showed is that, in fact, further. So let me write further strengthening of these primes. So P in this arithmetic progression, okay, I will call this AP here. AP means this particular arithmetic progression is actually infinity. So in fact, he showed that this particular arithmetic progression will be in fact it will be like infinity. So this is like a stronger statement than that. In fact, there is an even stronger statement, which I will mention shortly, but I don't know how much of this we will prove. Okay, so we'll definitely prove this. We'll definitely prove this, but so in fact, one can go even further. There is an even further. So before I state that even further, let me go back to Euclid's proof. What did he show? He in fact showed that if you take primes like this, I mean, the sum is divergent, but how is it divergent? Okay, so what did Euler show actually? Euler in fact showed that if I take primes less than equal to x, 1 by p, how does that go? Okay, so what he showed is that I think, okay, I may be writing something wrong here, so let me see. So does somebody remember if I'm writing the correct statement or not? Anyone here who knows? Is this the right statement? Sum of one reciprocals of primes. If I take, it is a more quantitative statement of saying this is divergent, right? You know, summation 1 by n less than, I mean, is divergent, but a better thing to say is if you add reciprocals up to some x, then you get something like log x, right? So you know that. So similarly for primes less than equal to x, actually let me check this statement because I don't want to say something completely wrong.
I think it is log x because this is Merton's theorem, right? This thing what you're writing.
Oh, sorry, it is log, right? Okay. Yeah, I am forgetting. Yeah, so pKs are like, yeah, you're right. Actually, it should be log. But let me just see even the constant if it is correct. I should have come prepared. Sorry about that. Can someone? Yeah, it is actually log. In fact, it is going like log. That is actually the correct statement. So I'm checking in Wikipedia. There is a statement, and sorry, yeah. So as you said, so this is log. Actually, yeah. Anyway, the thing that I wanted to say, I could have stated without this. So, in some sense, so what is the second statement? This is going like this. So the further statement that Dirichlet proved is not only that there are infinitely many primes here and infinitely many primes. So I'm just saying for 1 mod 3, but you can think of more general situations. But for 1 mod 3 and 2 mod 3, not only are there infinitely many primes, there are equal number of primes. So what does that mean? That means if you take p less than equal to x. Okay. So what is it for this? At least let me not just to not make a mistake. Let me write p congruent to k mod m. Let us say. Okay. So let's take arithmetic progression of this form. It is k mod m. But then you sum all primes up to x. See, when you take mod m, what are the mod m? When you look at modulo m, so you have 1 mod m, 2 mod m, or 0, 1 up to m minus 1 mod m. Some of them we have to leave out. How many will you have to leave out? Anything that has a common factor with m is a problem, right? Not only is 0 a problem. So for example, if you take m is 4, not only 0 mod 4 is an impossibility, 2 mod 4 will also be an impossibility because those are even numbers. So you have to leave out all those that are co-prime to or have a common factor with m. So you have to leave out those k for which we are basically taking k plus multiples of m, right? So k and m have to be co-prime. So the number of k less than equal to m such that k is co-prime to m, that is usually denoted phi of m. Okay, so that is Euler's torsion function. So that is the number of different sequences which are really there. So for example, when m is 4, then 0, 1, 2, and 3 are the possible modulus, and you have to remove 2, and phi of 4 is only 2. What Dirichlet says is that not only is the number of primes infinity, they are equal in all the remaining ones. Okay, so in other words, without any restrictions, this was going like log x. Now with the restriction, it will go like divided by phi of m. So it is kind of saying that equal number of primes in each of the allowed residue class. So you can just informally, that is what it is saying, that there are equal numbers in fact. So this is Dirichlet's theorem. Okay, so any questions, comments, etc. here? So I will come to that. So I almost don't have time. So let me just tell you how Euler's proof works, just because that will be a motivation for something that we will do. So just a quick recap of Euler's proof. So the great formula that Euler started with is the following, that you can consider 1 by n to the power of s. So you can take s to be bigger than 1 so that this is convergent. Okay. So this is same as product over primes 1 plus 1 by p to the power s plus 1 by p to the power 2s plus dot dot dot. Now why is that? Because when you multiply this, so you take a few prime powers here. So you may take, so if n is, see, if n is p to the e1 up to pk, p1 to the e1 up to some pk to the ek, right? So how will you get 1 by n to the n to the s? You will take, in the first one you will take p1 to the e1s, in the second you will take p2 to the e2s, etc. When you multiply this, it's kind of, everything is infinite. You need to justify convergence things and interchange of all these summations properly. But it is at a heuristic level, it's very clear that when you multiply out, every number will occur exactly once. And then this is actually fundamental. Here it is fundamental theorem of arithmetic actually. This is fundamental theorem of arithmetic, that every number is uniquely represented as a product of primes. Now this is a geometric series, so you can write this as product over p 1 over 1 minus 1 by p to the power s. So this is how you get. Therefore, so this is usually denoted zeta of s. So let's take log of zeta of s is sum over primes negative log of 1 minus 1 by p to the power s. Okay. So you know that log of 1 minus x is minus x squared by 2 minus x cubed by 3, etc. Power series expansion for valid for mod x less than 1. So which is, will not worry about various things. So all the negatives cancel. We get 1 by p to the s plus 1 by p to the 2s plus 1 by p to the 3s plus dot dot dot. Okay. So now each of these is convergent.
So Manju, you're missing the 2, 3 and all those things.
Okay. So 2, 3, etc. Okay. So we will write this as summation 1 by p to the s p plus some big O of 1, which is bounded.
It's 1 o'clock.
For all s greater than or equal to 1, let's say. So it is bounded irrespective, because you get a square, cube and all that. So this part is bounded. So of course there are infinitely many of this. Do we get this? Let's not worry about that. That's easy to fix, but more or less we have it here. So now as s goes to 1, as s decreases to 1, zeta s goes to infinity. So log zeta s goes to infinity. Hence, summation 1 by p to the s also goes to infinity. So this implies that summation 1 by p must actually be infinity, because that beats all this. For any s bigger than 1, it beats this. And if this goes to infinity, this must be infinity. Okay, that is Euler's proof. All these actually are important ingredients. We will do it in more generality and we will fix the convergence issues, etc. Okay, sorry, I'll stop here now. But if there are any questions, please ask.